The title of the tutorial is Integrating Terrestrial and Non-Terrestrial Networks, 3D Opportunities and Challenges. The presenter of the tutorial will be kindly Dr. Giovanni Geraci. He's the head of telecommunication engineering at University of Pompeo Fabra. He's also an assistant at that university as well. He was previously with Nokia Lab Bell, and he holds a PhD from University of South Wales, Sydney. He's also a co-inventor of a dozen of patents, and he's also a distinguished lecturer at the IEEE ComSoc Society and the IEEE VTS Society, and a co-editor of the book UAV Communication for 5G and Beyond. And he received the IEEE ComSoc EMA Outstanding Young Researcher Awards. And yesterday he was one of the winners of our competition. So the floor is of you, Giovanni.
Hello. Hi. Thanks very much, Dr. Abdallah, for this very kind invitation. Is the mic working? Yes, fantastic. So it's my pleasure to be here and participating in this extraordinarily high level and high quality event where we've heard many distinguished speakers over the course of the first 2 days, and I'm looking forward to the third day. So today I'm going to give you a little bit of more of a research perspective on non-terrestrial networks and how they can be leveraged with or without terrestrial networks in the picture. So very briefly about me, I was very kindly introduced already, just to say maybe a couple words about the university where I work. I'm based in Barcelona. I've lived in many countries before, but I call Barcelona home now. It's a wonderful place to live. IE University is relatively young. It's about 30 years old. It was ranked among the top 10 worldwide in terms of young universities, so we do quite good research there. And we, broadly speaking, work on 6G and Wi-Fi 8, which is the upcoming generation. Well, the next generation of Wi-Fi is Wi-Fi 7, and then there will be Wi-Fi 8. These two would be commercialized around 2030, right? So if you're interested in collaborating with us, whether you know talented students who would like to work with us, or whether you want us to collaborate with you, please do not hesitate to get in touch. So also, please let me say thanks to some of the people I've been very lucky to work with over the course of the past few years. We've got collaborators both in industry and academia, for example, Ericsson, NYU in the States, UPF itself, Huawei, UC Irvine, Luxembourg, and so on and so forth. Right, so this is the outline of the talk. My plan is to structure the talk into 3 parts and to take short breaks after each of the 3 parts. And maybe we can have questions, I think. Because the 3 parts are kind of like self-contained. So if you have any questions, please keep them in mind, and then at the end of each of these parts, I'll be super happy to interact with you. Let's make this interactive. I mean, let's not make this one way, really. I think many of you are very familiar with the topic, and I want to learn from you as much as I want to share my knowledge with you, okay? So the first part is about non-terrestrial networks, and I'll explain what that means. Basically, it means base stations or providers of connectivity in the sky. The second part is about non-terrestrial terminals. That means devices in the sky that want to be connected. And the third part brings the 2 parts together into more of a unified 3D vision. Okay, so if you by any chance attended my short talk this morning, this is a much longer version of it with many more technical details, which I hope you'll be interested in. Right, so just to make sure we're on the same page in terms of terminology, okay? So what do we mean when we talk about NTN, etc.? So here on the left, I put everything I think is a base station, and on the right, I put everything I think is a terminal or a user, okay? So we can have different non-terrestrial network base stations or cells, right? Satellite cells, either geostationary or low Earth orbit, high altitude platform stations, or UAVs acting as base stations. Okay, so I think we've heard extensively from experts in the field about these things between yesterday and today, right? So I will not go too much into the details, but you see that this creates kind of like a layered structure, okay? And on the right, we have users instead that fly, so non-terrestrial terminals. So now I'm seeing UAVs on the right as users, not as base stations. Why am I saying that? Because I imagine a future where there will be many use cases enabled by UAVs, many applications. It could be monitoring of infrastructure, pipelines, or even monitoring of crowds for safety, delivery of packages, or even delivery of people. We'll talk more about that later. And in this case, if you want to automate all these tasks and these applications, meaning having them pilotless, that's the only way, in my opinion, for the whole ecosystem to scale up. If you think of for each drone having one pilot, this is never going to fly, right? And so to have them autonomously flying, they need to be reliably connected to the network. That is the key, right? If not, it's not going to be safe enough. Even regulators are probably going to be reluctant to allowing this, okay? And so I want to highlight that there could be two types of traffic that we need to handle when we have these autonomous UAVs. One is the data traffic. We're all familiar with that in the comms sector, you know? High throughput in the case of UAVs, for instance, for video streaming, okay? Maybe the difference between our smartphones and the UAVs is that we mostly do downlink, whereas maybe the UAVs will more do uplink because they take videos and stream it back. But other than that, it could be similar in terms of requirements. But what's very different is what I call the command and control traffic. So this is the type of link that is required to support autonomous flight. Okay, so for navigation and things like that. This doesn't have a very high throughput requirement. You'll see, we'll talk about only 100 kilobits per second, for instance, but it has to be very reliable, as you can imagine, and the latency has to be met very reliably. Of course, we have other types of flying vehicles besides UAVs or drones, which are aircrafts and eVTOLs. These are obviously bigger vehicles. In that case, besides providing connectivity to the vehicle itself, we might want to provide connectivity to the passengers inside the vehicle, right? So that changes the requirements as well. So the first part of my talk will focus to what's on the left. I'll put the spotlight on this one first. Okay, so let's talk about non-terrestrial networks. A little bit of a very brief history. So I will focus mostly on satellite communications. Why? Because, not because hubs are less important, but there's been more interest in the standardization bodies and 3GPP on SATCOM first. Why is that? Because satellites have already a base of manufacturers, operators, and customers. Okay, there has always been a base of manufacturers, companies that make satellites, companies that run them, providing services, and companies that use these services. Of course, with some limitations. But why has this been not so successful so far? So even though they've been around for over 50 years, mostly we've been working with geostationary satellites. Whereas nowadays we all hear more about LEO constellations being launched. And it's been for services like navigation, weather monitoring, etc. Whereas now we hear more and more about broadband, okay? The deployment cost has been always very high. At least myself, I've always associated satellite connectivity with something I cannot afford, right? And there's been a lack of a unified standard, meaning there's a standard for mobile networks driven by the 3GPP, for instance, and there's other standards proprietary sometimes for satellites, right? But these things are changing as we speak because mobile broadband now is a service that satellite operators have in mind to provide, okay? Which is completely different than weather monitoring, right? And as I said, LEO constellations now are being planned and satellites are being launched at a much, much cheaper, in a much more affordable manner. And now there's a marriage between the cellular and the satellite industries, and this is wonderful because if we have a unified standard, that means that with the same off-the-shelf terminal, with a 5G phone, we'll be able to connect both to terrestrial cells and non-terrestrial cells. You can imagine how important this is to reach more and more customers, right? So here I want to just showcase some of the use cases that the industry had in mind when they first planned this integration, this 3GPP integration between cellular and satellite. These use cases do not really sound so futuristic because they are more short-term and they trigger and motivated the first stage of standardization. I guess release 17, this is what we're talking about. So the first one is called service continuity, quite self-explanatory. For example, roaming between a terrestrial and a satellite network. So here, look at this drawing, you know, you are You're in the city, you're connected to terrestrial operator A, and then you're off at sea, you lose that connectivity, but maybe you can be connected to a satellite operator, okay? This doesn't necessarily have to be a passenger, it could be a cargo ship, you know? You want to keep track of your merchandise wherever it is in the ocean, so you don't lose that connectivity. And then when you reach the destination, then there's a new terrestrial operator that provides network, okay? Then service ubiquity. Ubiquity from Latin means everywhere, right? So imagine that we are in a rural area where the operator is reluctant to lay fibers because they're too expensive or they take too long. So meanwhile, solution for that could be to provide backhaul over satellite, okay? So you still have towers, but you don't need to dig anything because you can provide backhaul. And then the signal is relayed by these base stations to some users in the sparsely populated area, say. Of course, this is much quicker and economical than optical fiber. It could be a temporary solution, say, but you incur a larger propagation delay from a satellite. But we'll see that this is not so bad, especially in the low Earth orbit, because they're not as far as we might think. Third use case is scalability. So imagine that you have popular content that you want to deliver, okay? So when you want to deliver the same data to many, many users, what can that be? For instance, some software update for self-driving cars. Think about that, okay? Then a very efficient way of doing that is to do it TV style, just broadcasting the same data to everyone. So for that, satellites could come very, very handy because they have a huge footprint and they can reach many terminals in a very effective way, okay? So this could avoid network saturation because you offload that traffic from the terrestrial network, so you avoid the network being saturated. Okay, so now let's go a little bit into the details. Now that we talked about the use cases, I'll mention more futuristic use cases later in the third part of the presentation. So what does this non-terrestrial network architecture look like? Here there's a schematics. So we have on the bottom left of the image, we have the terminals. So you see there's two types of terminals, either handheld, which could be a phone or an IoT device, right? Basically a terminal that does not have a big antenna. A terminal whose antenna is omnidirectional or semi-directional. The alternative is a VSAT, a very small aperture terminal. This is a terminal that has a very directive antenna, so it has a very good antenna gain. And that is going to be important if you operate at high frequencies because the propagation loss is higher. You need to compensate for that, so you need a very good receiver. Okay, I'll say more about that later. Then you have the service link, which connects the terminal to the satellite, for instance, or the HAPS, if it's a HAPS. You might need to have an inter-satellite link in some cases, and then you close the loop with a feeder link that connects you to a gateway on the ground and then to the core network. Okay. In what cases do you need an inter-satellite link? Well, imagine that you're in the middle of the ocean, then there's no gateway. So before you reach a gateway, sorry for that, before you reach a gateway, you need to connect to another satellite. You need to kind of like relay your signal. These inter-satellite links can be RF or could potentially be free space optics, okay? Because the conditions are good. Depending on the altitude, you know, there's no atmospheric phenomena, so it could be good for free space optics. So I already mentioned how important the frequency is. So when we operate at higher frequencies, you need a terminal with a very large antenna gain. Here I put 40 dBs, okay? Then there's different types of payloads. We don't have time to go into the details. Basically what this means is that you could have the physical base station on the satellite with full functionality, digital signal processing, regenerative, okay? Or you could just have a repeater on the satellite, but the actual base station and the baseband things are done on the ground. It's two different types of architecture, okay? So they have some implications, but I will not go into the details of that. Okay, here, for some of you who might be interested in doing performance studies or simulations, I wanted to summarize what can be found in a 3GPP document that is more than 100 pages long, okay? So the 3GPP defined some deployment scenarios such that companies could run studies and simulations, okay? So as you can see, there are many combinations of different parameters, okay? So I tried to kind of like tidy things up on this slide. We need to choose what carrier frequency we're considering, okay? What band, how large the bandwidth is, what type of device we assume the user, okay? And what type of platform up in the sky. right? So all these different combinations that have different deployment names in some tables in the 3GPP technical reports. But just briefly speaking, you can work at lower frequencies in the S band, which is at 2 gigahertz, okay? Similar to the frequencies our mobile phones use, for 4G at least. Then the band available is very small, okay? We're talking about tens of megahertz. Or you can work in what's called the K band, so at the 20 and 30 gigahertz, okay? In that case, downlink and uplink, they're quite separated. The bandwidth is much larger there, you know, we're talking millimeter wave there, so you have much more band. What's the problem? The problem is there's more attenuation. So your signal will not reach unless you have a VSAT, like a very small aperture terminal, which has a very good antenna gain and can compensate for that. Okay, so as you can imagine, you cannot put that on a mobile phone. You can put that on the roof of your car or on a ship, right? But not on a mobile phone. Then you can have geostationary or LEO satellites, for example, and then the same thing applies to HAPS. There's just some difference in terms of what frequencies the HAPS will use. Because as far as I understand, HAPS might work in the same band as the terrestrial network. So that means that you should not have a HAPS too close to a city, if that's the case, because it would interfere. Whereas a LEO satellite uses a different band, so even when it's passing on top of a city, there's no interference. It's a different band. Right. So some key features of non-terrestrial network communication. So if you've been working on terrestrial networks like me, I've been working mostly on cellular deployment studies. Then when I moved into this, I had to understand the key differences. What makes it so different? So here is a list of 4 key differences. One is that SATCOM requires line of sight. You cannot be indoor if you want to be connected to a satellite. So because the link budget is already so tight that wall penetration is going to kill your signal, okay? So here, this picture, this image shows you the received signal strength, a comparison between what happens when you're connected to a terrestrial network. This is just an example, okay, with these parameters, 2 gigahertz, 10 megahertz band, urban macro, outdoor. So this is kind of like the range of power you receive in dBm, and you receive much less from a satellite, okay? And if you're in no line of sight, you really receive too little. So it has to work in line of sight. The delay, of course, they're far away. The signal takes longer to propagate. So, but the delay is not so bad after all, because we're talking about tens of milliseconds, which is actually not so much more than what you typically experience in LTE. Okay, so this is not a geostationary satellite. Geostationary satellite takes half a second. This is something different. So unless you're doing remote surgery, I think that lots of applications would work with LEO. That might not be the showstopper. There's a large Doppler shift due to the movement. So, you know, Doppler effect occurs when transmitter and receiver are in relative movement. Like, you know, like the sound of the ambulance. When it's approaching you, it's higher pitch, and when it goes away, it's lower pitch, right? Same thing for the electromagnetic waves. The thing is that here we're talking about so much more Doppler effect because these satellites move really, really fast with respect to your position on the Earth. So in a typical terrestrial network, even if you are at 120 kilometers per hour, your Doppler is around 200 hertz. And with the LEO satellite, it can be around 50 kilohertz. It's a whole different thing. So the 3GPP has been working a lot on fixing this problem. I will not go into these details because it's more engineering than research, but it's an important problem that has been addressed, for example, using larger subcarrier spacings, you know, so one subcarrier does not interfere to another, okay? You can also pre-compensate this because you know where the satellite is going. The orbit is defined, so you can kind of like predict this Doppler and compensate it. And last but not least, we mentioned it, additional attenuation. So the signal has to travel a very long way before reaching us. So it undergoes different stages of propagation that a terrestrial signal does not experience. So you have atmospheric attenuation, scintillation, which brings about very interesting phenomena in terms of fluctuations of the signal. And then clouds and rain could affect this depending on the frequency. You know, the millimeter wave is typically more sensitive to these phenomena. And also, as you see, On the terrestrial network, we typically have much more scattering, multi-path, different paths of the signal reach the user. This is not really the case, or at least not as much from a non-terrestrial network terminal base station. So a key parameter when we study performance or design the system is the elevation angle. What's the elevation angle? If this is my terminal, it's the angle at which I see the satellite. So you draw the horizon line from wherever you are, and that's the elevation angle. So what's a good elevation angle? 90 degrees. It means the satellite is on top of the terminal. That's the perfect situation. As this angle gets smaller and smaller, things get nasty because the satellite gets further away, so there's more path loss, plus there's a higher chance of being in no line of sight because you start having obstacles in between. Okay, so the closer to 90 degrees, the better, and I will show you some results that prove how important this is. And then related to this, you see, depending on the elevation angle, there's a certain geometrical coverage of the satellite. So at some point you will fall outside that, obviously. Basically, the satellite sets, just like the sun, right? And this geometrical coverage is typically very, very large because 600 kilometers is quite high, but you don't necessarily want to use all that coverage. It's not so good. Typically, you want to focus your power into a smaller area because you want to reuse your frequency to serve more than one user at the same time. That's what's called the radio coverage, you see. So you make the radio coverage small by focusing the power. For example, with directive antennas or multiple antennas or technologies like multi-user MIMO, etc. So I just wanted to mention that. And another important parameter is the beam frequency reuse. So if you have a satellite, you typically illuminate the ground with several beams, 7 for instance, and then you have different choices. You're giving a certain bandwidth because the handover command doesn't reach because you're already deep inside into the other cell, and then your SINR is too low to receive this handover command. Then the user disconnects and has to connect again with initial access, which again is a lot of signaling and overhead. You don't want that. So what's been introduced is what's called conditional handover. It's a different approach to handover, where the network sends a command with a condition. So the network instructs the terminal and says, listen, keep measuring the power that you receive from all the cells you have available, and when these conditions are met, transfer to the new target cell. So why is that better? Because there's no need for a specific handover command that might get lost. So this is a solution that has been introduced in the latest releases of 5G Neo Radio. Okay? But mobility management is a very interesting problem for non-terrestrial networks if you're doing research. I want to conclude this first part of the tutorial talking about some business aspects. I know I come from academia, so perhaps I'm not the most qualified person, but I do have some personal ideas that I want to share with you, which is what could the showstoppers be for this vision of non-terrestrial networks, particularly LEO. Okay? It's a bit of a problem to show this slide in the other room of the conference, so I'm showing it here. Providing LEO broadband, as I will show, might require a VSAT. Why? Because you might really want to work in the high frequencies where there's a lot of band. But if you do that, you need a VSAT, okay? This bulky receiver, because it has a high gain and it has also beam tracking capability, okay? So this is a cost challenge at the end device because you're putting this burden onto the user. The user has to buy that. So if you know Starlink works with a terminal like that, they open it, they have a dish, they put it on the roof, okay? So not everybody is going to be able to afford that. And this is not competitive if there is fiber or a high-speed cable. Of course, it's competitive if there is no fiber there, right? So the potential is to offer broadband connectivity where there isn't any. We all know this by now. And because it has a fast time to service as well compared to fiber, okay? And the good thing is also the future devices, because of this huge standardization effort in 3GPP, will have a dual capability, cellular and satellite access. So once again, off-the-shelf phone will be able to connect to both. Then what data rates they will achieve, that I'm not entirely sure. And on the other hand, I wanted to mention what potential market segments there would be. And the focus of this conference has been on the most noble of such market segments, which is to connect the people who are not connected. And I could not agree more on that. I've seen a lot of parts of the world throughout my life where really connectivity is non-existent for different reasons, geographical or economical. So that's the second bullet you see on the list. Uncovered areas, you provide basic communications to developing markets. Limited revenue, I wanted to put there. Limited revenue for two reasons. Maybe because sometimes these countries are not fully developed, so the economical capability of the users is limited, but also because there are not many users inherently. If the area is remote, if there hasn't been any TN deployment, it's probably because there are not many users, okay? But there are also other possible markets to offer guaranteed service. So you have a user that is already connected, but for example, this person, like in Europe, you know, people like to go hiking in the mountain a lot, okay? And the mountain, you typically don't get service. So near Barcelona, we have very beautiful mountains, and it would be good to have this satellite connectivity just in case, in the case of an emergency. Maybe you cannot make a video call, but you can send a message at least, you know, and send your position, etc. And the third one I listed is more like for companies, for enterprises. So enterprise IoT connectivity. Remember the slide with the ship I was showing, you know, maybe for containers, vehicles, vessels, you want to track those when there's not a terrestrial network. So the NTN comes into picture there. And this we've already discussed extensively. The type of service that's fixed broadband at millimeter wave, let's say 20 or 30 gigahertz. It requires a device like this. And there's direct access to a handheld terminal or IoT. This is for outdoor because the penetration loss would probably be too much for your device. And the advantage of this is that very soon you can do that with a 3GPP compliant end device, once again, thanks to the standardization effort. So this is the end of the first part that I had in mind on non-terrestrial network. So if you have any questions, I'll be really delighted to kick off some interaction on this.
Thank you, Gio, for the great background and introduction. So my first question is regarding VSATs. So is there any way that we replace these VSATs with, for example, these reconfigurable intelligent surface technology, like passive devices on top of the building? And is it possible? So why do we need to, why? Because the technology of these VSATs or any dish antenna, right? So we have a certain angle, and the incoming signal is directed to a certain point, focus, and we have the feeder gets all the signal, and it's like, you know, improving the signal that way. So is there any possibility to use reconfigurable intelligent services, or are there any work considering this? This is my first question. The other question is regarding the inter-satellite crosslinks. So what I heard from the Thales is they are mentioning the crosslinks between the satellites through dish antennas. I think they are planning or building these VSATs on different surfaces of satellites to facilitate this interconnectivity. So do we have any idea to implement the same kind of beamforming technology instead of having these mechanically steered VSATs? Why they mention in their satellites, they have really mechanically steered VSATs on top of the satellites. So I mean, with respect to satellite technology, to be honest, and the level of wireless communication technology we have, it is like very primitive.
Yeah, is it working? Yeah. Thanks a lot for the question. Yeah, both very valid questions. So regarding the risk, the reconfigurable intelligent surfaces, I think it could be an alternative. You need to see the efficiency though. So let's think about it. Where would we deploy them? They're supposed to reflect the signal. So the VSAT is facing up because it can capture as much energy as That's what a VSAT does, just in a different way. It's facing up and it's focusing all the signal. It's like a parabolic dish, right? So in that case, there's no difference. If you're talking about RIS proper, then it's supposed to be passive and it's supposed to reflect the signal. The problem I have there is it cannot face up and down at the same time. So it's supposed to reflect it down, but receive it from up. The only way is to put it like this, like on a wall. But then the angle is not very good at all. Yeah, I think that might work actually when the satellite is not close to 90 degrees. So if the satellite is about to set, but still in line of sight, that might be a smart idea. But if not, if it's supposed to do processing, well, it boils down to a VSAT once again, I think. The second question you asked, from my understanding, the intersatellite link is not standardized by the 3BP. It's left as what do you say? I mean, proprietary solution, right? So implementation specific. So I think you can implement that however you want. And my speculation is that until we get to a large base of customers and a very good return on our investment, there's no point developing very sophisticated technologies for that. But of course, I think things will get better and better. FSO maybe is a good way to go. And also for the feeder link, maybe FSO, free space optics, is a good option. Does that answer your question? Thanks.
Hello, I have one question about the IoT devices. Currently, as you know, most of the IoT devices are working with machine-to-machine SIMs, and they are using the normal GSM services. Is the market going to go through to VSAT technology sooner in the IoT market, or it will remain the same for very specific use?
Thanks for the question. So I think IoT is one of the market segments for sure. Well, a VSAT has a certain size. So if by IoT you mean sensors, I really don't see how you can put a VSAT, which could be the size of half of this table, on a sensor that is the size of a nail. So for this, so unless the application is very different than what I imagine, I think we're talking about direct access. And there's a lot of skepticism because of the link budget. IoT devices by default, they're power limited. So probably the transmit power is supposed to be really low. But what I know is that there are operators. There's one headquartered in Barcelona, by the way, that provide direct access to IoT devices from LEO satellites. So it means, I guess, that the link budget can be closed somehow. Probably you have to put the burden on the satellite. You need to have more directivity at the satellite to make sure that you receive this uplink. I suppose the uplink is the problem there. Downlink, you probably have more power budget. Does this answer your question? Thank you. Well, then in that case, if it's big enough to fit a VSAT, then I suppose so. But the VSAT mostly comes for broadband. And IoT usually is not a use case where you need broadband, right? So that's why I don't know if it would justify the cost and the real estate it takes to install the VSAT, at least for what I have in mind. But maybe, yeah.
Thank you. Mine is, you well described the technology and the use cases for what you just indicated, but it has to be something that is business worthy. If you are mixing satellite and terrestrial we get it very cheap. Where I come from, it's less than 20 cents reals. If you mix, and satellite there is specialized market, it's a bit costly comparably. If we are to mix, what is it that is, maybe this question is for the operators and the system developers. What makes it so expensive? What will make it cheap so that I get similar per minute charges so that it becomes more useful?
Nothing. That's my answer. Nothing will make it as... This is physics. We cannot beat physics, right? So the difference between a cell that has a size of 1 kilometer and a cell with a size of 100 kilometers, how can you beat that? So if you reuse the chunk of if you have a cake and you share it with 10 people, it's not the same as sharing a cake with 10,000 people. You're going to eat much less cake. I think you cannot beat that. But going back to the beginning of your question, it's very valid, which is why should I use the satellite if I already have terrestrial network connectivity? My point is the satellite will not be put there for me who already has terrestrial connectivity. Maybe it will be put there for somebody else who doesn't. But because it needs to orbit, inevitably, at some point, it will serve me. So why not using it? In that case, you can think of it as coming for free. So if you think of it as a real estate, like a cell tower that can be leased, rented to different actors, just as it traverses the sky at different times, it's kind of like combining that revenue for whoever is operating that. So this is what I'm thinking about, and we'll go back to this in the third part of the tutorial, if you're interested in it. Thank you.
Thank you. Thank you very much for your presentation. I have a quick question regarding the frequency. If we're talking about the coexistence of NTN and terrestrial networks, so when we talk about millimeter waves, there are some frequencies that are favored in the case of like terrestrial networks, and definitely they're not going to be favored in case of an terrestrial network. Is it, I mean, can you comment on the on having different frequencies for different type of networks?
This is a great question to which I only have a partial answer, and actually I would have loved to hear more about this from people who work in this. So my understanding so far is that for sub-6 gigahertz, let's start from that, there's going to be different frequencies. So the terrestrial operators have their own band, and then for satellites, there's going to be another dedicated band. Of course, for the terrestrial network, this can be country-specific, but for the satellite, it cannot be country-specific because the satellite will go everywhere. So there's this designated band, and I'm sure they're fighting for more. It's called the S-band. They're orthogonal. So there's no coexistence problem. From a research perspective, we can, of course, imagine what would happen and come up with smart algorithms and cognitive radio and all of that. But so far, this is totally beyond reach. I've asked, for example, some people that work at Project Kuiper, you know, Amazon's constellation. One of the, actually the director of engineering, I had the chance of asking him. They're not thinking of that as of now, separate bands, okay? And regarding millimeter wave, I think also it has to be different frequencies. Maybe over there, we could think of reusing it because millimeter wave is typically a very directive link. So typically there's less spillover of signal. So in that case, maybe there's more opportunities. But there already are many constraints on millimeter wave communications. I think, at least in Europe, even for 5G millimeter wave, you're not allowed to radiate above the horizon, for example, because there are some incumbent services like fixed satellite services and stuff like that that you could potentially interfere to. So yeah, very valid topic. I don't have the definite answer, and I think nobody does yet. I think it's still a topic for debate.
Yeah, I think I might add something here. There is a debate in certain frequencies. 28 gigahertz is one of them. And of course, there is another portion in the C-band. But in the C-band, the satellite operator are using it for the uplink, so it's not that much difficulties. But in the 28 gigahertz, where the IMT now, or the 5G will start, they have a plan to do 5G equipments, especially the standalone equipments for the private 5G in the 28 gigahertz, and there is now a strong debate on that band as well. So there is a debate, but the beauty of the satellite industry, they are using FDDD more than the IMT or the mobile, which mostly rely on TDD. So in FDD, sometimes the uplink you have no problem, but the downlink is quite problematic.
Yeah, very valid point. Thank you, Dr. Abdallah.
I think now we
Move on.
Yeah, one more question, or we can
Maybe
have a
let's
break?
move on. And
Let's move on. Okay.
Yeah.
Okay.
What do you think? Right. Thanks a lot for the great interaction. I love that. And I hope we'll have the same in the second part of the talk. I'm talking about something slightly different now. So as I promised, now I look at non-terrestrial terminals. In particular, I focus on UAVs, and I focus on how terrestrial networks could provide connectivity to UAVs. I've been working on this for the past few years. I just have some condensed results, not to overwhelm. If you're interested, I'll give you references to the papers, okay? So why UAV communications? I'm trying to take the perspective of a mobile network operator here and why we would want to connect UAVs. This was initiated around 2017 with a study item on LTE support for aerial vehicles, okay? And so the pursuit of revenue, as I told you at the beginning, is not just to handle the payload, the data traffic of a UAV, but it would also be to handle the beyond visual line of sight command and control. So this C2 means command and control, okay? It's 3GPP terminology for that. This could open new markets and new opportunities because then, as we're dreaming of, then we could have autonomous UAVs flying reliably supported by the network and so on and so forth. Of course, what is the dream? The dream is always to get things for free, so to seamlessly reuse the existing infrastructure or the one to be deployed anyway for the ground users, also to support UAVs. The reality is that it doesn't work very well. We must prepare the ground, as I like to put it, to accommodate these aerial users. So in this table, which we don't have to go through in detail, these are some 5G ready use cases by the 3GPP. So if you're interested in doing some studies, you have some requirements in terms of end-to-end latency, the reliability required, and the data rate. Notice two interesting things. The top part of the table focuses on the command and control link. So there's requirements for command and control. The bottom is for application data, okay? And they're completely different because the application data maybe has a higher rate. For example, this 4x4K AI surveillance needs 120 megabits per second, but the other one has reliability requirement mostly and some end-to-end latency to be met, okay? So now I would like to describe two main issues. So now I claim that it's difficult to support UAV users with terrestrial networks. There are two main reasons, in my opinion, why it's difficult. So the first problem is the problem of initial access and mobility. What is initial access? It means I turn on my device, I look for the best cell, I connect to that. And then, as I keep moving, I switch to the best cell that I see whenever I move. This works very well with our phone. It doesn't work well with UAVs. Why? So the way it works with our phone, so here I'm showing you the perceived antenna gain for a device at 1.5 meters. So it's a 1.5 meter UAV, it could be my phone, okay? It's the same thing. So this is the distance from the base station. Imagine that you are in front of the base station at the bore site and you move away, okay? And then this ripple is when you're too close to the cell. It never happens, you're never so close to the cell. Here you are right under the beam, you get a very good antenna gain, and as you move away it gets worse and worse. Fair enough, at some point you're going to see another base station, you will switch. So this works very well, that's how the network was designed. For the drone, it's completely different. The drone is higher, it will never be illuminated by the main beam of an antenna array. It will see all these side lobes, okay? So look at this. So there's very high fluctuations and there are peaks and notches. This is really something you don't want. So basically, the result of this is that the UAV typically would not connect to the closest base station, but actually to a base station far away, maybe because it intercepts a lobe from that. I mean, simply speaking, imagine you are right on top of the base station, you don't get any signal at all. So it's not a matter of distance-based association, okay? So this really changes the rules of the game. And this is a picture taken from a paper by Ericsson. So here basically there's a bunch of cells, and for each point on the map, the color represents the best cell. You can see how often this changes. So as the UAV moves, this UAV was at 50 meters only. The higher you are, the worse it is. As you move, you will have to switch cell all the time because you go from one side lobe to another, to another, to another, and you will have to switch cell all the time. This is terrible, right? Because the UAV will not associate to the physically closest cell. So it will do many handovers. What's the solution to that? 5G new radio gets better. So I don't know if you're familiar with it, but in 5G new radio, there's this concept of SSB, synchronization signal blocks. So instead of illuminating a cell fixed, now there are beams that you sweep in time, okay? It's like looking for users, you know? It's like sending a cell reference signal, typically into 8 directions. I've talked to vendors. They say that typically they have a code book with 8 beams, or up to 16, I think the standard supports. So this works much better because potentially, if typically these beams, of course, they're placed down, okay, to cover the cell, maybe some buildings. But if you could dedicate maybe one of those up to the sky, then the image we saw before would not occur anymore. This is what you would get. You would get something much more smooth because you get the beam of a cell, the green one, and then as you move, at some point, you get the beam of the other cell. So the transitioning is much smoother, and the mobility management problem would be alleviated. But still there's work to do. This is probably an interim solution. And the second huge issue is interference, okay? So when the UAV is high, it's higher than the buildings. So it sees many cells in line of sight. One might think, oh, that's good. I have many cells to choose from. No, because one cell will serve you and all the others will interfere to you. And these interference signals, they are comparable in strength. It's not like our phone. We walk down the street, we have a serving cell with a good signal. Any other cell by design will be attenuated much more because there are obstacles, it's in non-line of sight. There's a path loss exponent of like 3.5 or 4 in urban areas, okay? The signal decays very fast. So the good signal is much stronger than the bad signal. This is not the case here. The signals are very comparable. Even distance-wise, now you had the vertical component. So even if horizontally you're closer to a cell, but then you apply the Pythagoras theorem and you look at the 3D distance, the distances are all the same. The path loss exponent is around 2 because we're talking line of sight. Basically, the result is that you have an SINR with a useful signal and many interfering signals that are comparable to the useful signal. So this is a recipe for disaster. You have a lot of interference in the downlink, meaning from the network to the user. What happens in the uplink? So in the downlink, the UAV is the victim, okay, of interference. But in the uplink, it turns to the aggressor. Now, in the uplink, the UAV transmits, every cell hears the UAV, and this signal will overwhelm the ground user signals. So it's going to disrupt the ground user's service. And if you have more than one UAV, well, you accumulate that. So also, coexistence is really challenging. So that's why interference is a problem. Now I'm going to ask, how severe is it? I just want to show you a couple plots just to quantify it and how we can solve this problem, okay? So for that, I will consider 4 different scenarios, comparing them, okay? My baseline is what I call a 4G network, single user approach. There is no massive MIMO, there is no multi-user MIMO, okay? Each time frequency resource, we schedule 1 user, okay? There is no beamforming. We're only illuminating one sector like that, okay? So I call this non-directional because there's no beams. And I compare this to what I call 5G. Please, let me just call it 5G for simplicity. The main feature I introduce is massive MIMO. So now every base station has been upgraded to massive MIMO, and they use beams, okay? 8x8 array, 128 radio frequency chains, cross-polarized antennas, okay? So why is this better? For several reasons. The signal is stronger because I point at my user. The interference is less because I don't spill over to other users. And I have the multiplexing gains because I multiplex more than one user on a physical resource block. So for 3 reasons, I'm going to do better. Let's see how. So here, let's just go into the core of this. I'm showing you the 5% worst downlink SINR, okay, as a function of the UAV height. So the first thing I wanted to notice is that it goes down, because the higher the UAV, the more this interference phenomenon gets serious, because you see more cells. And I'm comparing in blue this single user 4G approach, and in red this Messer-MIMO approach. The threshold you see there is -5 dB. For me, that's a proxy for coverage. Whenever we are below -5 dB, things are getting nasty, okay? And you can see how Messer-MIMO helps you. But it still suffers, but it's much better than single user MIMO for those reasons. Stronger signal, less interference, okay? Thanks to directionality. Can we do better than that? I'll show you 2 more scenarios. Now, not only the base stations have antenna arrays, the UAV also has an antenna array. Small, 2 by 2 only, but it gives some directionality. So I'm thinking, what if the UAV also can focus towards the serving cell, okay? Can we improve things? We will see some gains. And then the ultimate approach that I proposed is to do interference suppression in the spatial domain. So I call this null steering. What does it mean? When you have an array, you have spatial degrees of freedom to focus your signal, but mathematically, you can also use them to suppress the signal in one direction, okay? So instead of using all of your radio frequency chains and your digital precoding to point beams, you use some of this capability to suppress interference to a certain neighbor, which is a user in another cell. So you need to be able to acquire channel state information and suppress interference to that user. I'm not going into the maths of this. If you're interested, we can talk about it. But this is going to pay off handsomely, because interference is the key problem, and you're going to address it with this. So I'll show you what happens here. So this plot tells you the percentage of UAVs that reach at least 100 kilobits per second, which is the requirement for the command and control link, okay? For the 4 different approaches that I have on the left, okay? So this is as a function of the height of the UAV. Once again, the higher the UAV, the worse it is, because there's more interference. And while massive MIMO, the red one, helps, it helps only up to a certain point. When the UAV is too high, there's too much interference. It's not able to have spatial resolution to handle all of that. But interference suppression really is the most robust of all of this. Even directionality at the UAV doesn't help as much. Okay, I could give much more details on that, but I don't think that's the purpose. I want to just give an overview of that. We have several papers we published on this. Just for completeness, what happens in the uplink? Because remember what I told you. In downlink, the UAV suffers the interference from the network, and in uplink, it creates it to the ground users. So here I show the rates in uplink for ground users and for UAVs as I increase the number of UAVs in a cell, okay? So in uplink, if you have more UAVs, it gets worse and worse. You have more UAVs interfering to the whole network, so of course things go worse, okay? But the baseline here is massive MIMO, and then the red is massive MIMO, but also the UAVs have a little array, and this is interference suppression. So once again, interference suppression really is the key if you want to scale up in the future with many UAVs per cell. I understand this is not practical as of now, but imagine you have a corridor with many delivery drones, you might easily get up to 5 UAVs in one cell, all active and transmitting signals, right? So again, interference suppression is needed. So we published a book recently on this with some colleagues from China, the US, and Singapore. So we try to give an overview of what happens in UAV communications in 5G and also beyond with more research ideas. And okay, I want to complement this with millimeter wave communication. So what I said so far had in mind sub-6 gigahertz and massive MIMO, but what happens at millimeter wave? So what is the reason for using millimeter wave? Because we have more band, right? We all know millimeter wave has very, very huge bands. And millimeter wave works well in line of sight. Millimeter wave doesn't like obstacles. But guess what? UAVs are usually in line of sight, so potentially it could be a good marriage, okay? So again, the dream is always the same, that if I deployed millimeter wave 5G terrestrial networks, can I also use them, to support UAVs? The reality is that it's, again, it's not so easy. There's no free lunch. So what we did is we wanted to evaluate the coverage and the rates in an urban area, because millimeter wave, you know, they're thought for urban areas, right? Small cells, high capacity. The problem is that in this case, there's no channel model. So what I told you before, we used the 3GPP model, but which was taken from this technical report. But for millimeter wave, there's no channel model for UAVs, because this document has the millimeter wave channel model, but it's not for UAVs, only for ground users. And this is for UAVs, but it was not calibrated at high frequencies. So we had to come up with our own channel model, and this is the approach we used. We used a machine learning based approach. So this is what we did. We did this with colleagues from NYU in Brooklyn. So we took maps of cities, we ran ray tracing on those maps, we collected data. We trained a generative neural network based on these data. You know, ray tracing takes a very long time, okay? So we did this offline, and then the generative neural network will generate channel realizations very fast with the same statistics as the real data, okay? What will it produce? For each path that you want, you set the location of the transmitter and the receiver, and it will tell you if it's in line of sight or not, the path loss, the delay, the angles of departure, the angles of arrival, and so on and so forth. And then you can carry on your studies for coverage and capacity. That's what we did. And we did this considering two types of cells. We considered the standard millimeter wave cells and also some rooftop cells dedicated to UAVs. I will talk more about that later. So briefly, just to understand how it works, we use a two-stage generative neural network. The first stage will predict the line of sight or non-line of sight condition. Once you have that for the link, the second stage, so you give as an input the line of sight condition and again the positions of transmitter and receiver, okay? And then the neural network will tell you all the path parameters. The delay of each path, the angles of departure, arrival, elevation of departure, elevation of arrival. Okay, and then from that you go on and do your studies. And this is what it looks like, for example. So here we have on the left the data, on the right the model, they're very similar. On the top for the rooftop cells, on the bottom for the street level cells. So this is the probability of line of sight. Blue means non-line of sight. Yellow and up means line of sight. So you see, for the standard base station on the street, the moment you move away, this is horizontal and this is vertical. The moment you move away, you get in non-line of sight very soon, right? On millimeter wave. If it's dedicated, if you move away but the drone is high, you can still get line of sight. Okay, so basically, this has a physical meaning. It captures the real phenomena and everything. I have more plots on the angle distribution, but that's a little bit more difficult to explain. And we have this even on GitHub, and we published it recently. So this is for the city of London, but the study was done for Beijing, Tokyo, Moscow, Boston, and a bunch of cities. And then from that, what you do, you take all the paths, you account for the pattern of the antenna, the receiver, and you calculate the path loss. And this is a comparison between the path loss from the model and from the data. And there's a very good match, and also it captures some two-slope behavior that is typical when you transition from line of sight to non-line of sight, okay? There's this knee in the curve, in the blue curve. But let me move on for the sake of time and just show you whether it works or not in terms of coverage. So we consider the millimeter wave cell, we consider the UAV. This time the UAV needs to have an array because it's millimeter wave. If not, you cannot close the link budget. And the array is facing down, okay? So we consider these UAVs at different heights, between 30 and 120 meters, and we studied the coverage. Let's not go too much into the details. I just want you to see that the SNR is good. The SNR is good. There is good coverage. Blue is UAV at 30 meters, red is UAV at 120 meters. In all cases, even when they are in non-line of sight, there is good coverage. Why is that? We found out that sometimes the reflected path is not bad at all. So even with a reflected path, which is the lower part of the curves, still you reach the UAV. So this was quite interesting for us, yeah, that the side lobes and the reflections enable coverage. So it could potentially work, okay? I'm not saying that it's easy to do millimeter wave UAV, but from a system level point of view, it could work. And then we did another study recently, like this year, for capacity, okay? So here I just want to say that for capacity, we consider multi-user MIMO. So UAV, multiple users multiplexed from 1 to 4. So when you multiplex more users in the uplink, you have more interferers. If each base station is serving 4 users in uplink, there's 4 times as many interferers all along around the network. So the SINR gets worse. The SINR goes down, okay? But it doesn't go down so much, and so the multiplexing gain more than compensates for that. Because, you know, the data rate from the Shannon formula, you have a linear gain, which is the multiplexing gain, and the SINR is inside the logarithm. So it's worth it to lose a bit of SINR if you have a 4x gain, okay? So in terms of rates, they're increasing. So even MU MIMO on millimeter wave for UAVs might work very well. And so if you want more of this, if this wasn't enough, we just published this communication service and tutorials paper with some colleagues. So the paper is called A Flight from 5G to 6G. So this kind of like summarizes all our recent work on UAV communications from different perspectives. We even talk about cell-free, terahertz, RIS for UAV. There's a summary of what's going on in the standard. It's about 30 pages with about 30 technical plots. So if you're interested, you can go to this. And I think, yeah, this is the end of the second part of the tutorial. And then in the third part, we're going to try to put the pieces together into a unified 3D vision of the network. If you have any questions, I think this would be a great time to hear what you think about this. And maybe there was a question from the remote audience on conditional handover. I will address this question first. And the question is, can conditional handover be used to prevent a too frequent handover in LEO? Does it trigger signaling load to define more than one candidate target cell? Okay, very good question. I'm not sure if you can prevent the frequent handover. I mean, if a satellite disappears, I think we have to switch to another satellite. There's no other way. But the conditional handover perhaps could alleviate the radio link failure problem, meaning that if the user already knows that it has to switch to another cell, perhaps it doesn't need to report the measurements too often to the network. It can just collect the measurements and then make a decision, and it doesn't incur the radio link failure problem, maybe. Yeah, more than one target candidate cell. I think this is necessary. You need to identify more than one candidate target cell, just to be sure that you will find a proper cell to be handed over to when the necessity occurs. Any questions from here? Yes. Yeah, most of the people connected remotely. Yeah, thank you.
Assalamu alaikum. Yeah, my question about UAVs and NTNs in general, because the most dominant is the line of sight scenario, especially for satellite, and also UAVs. But for line of sight, we will lose the MIMO techniques benefits. So how to get that benefit of throughput from the line of sight scenario?
This is an excellent question, which would really take too long to reply properly. I'll try to maybe give a hint of what I think. From satellites, I think there's nothing to do. We need to work in line of sight, and the implication is that you will have one stream per receiver. So even if your receiver has multiple antennas, you cannot send multiple streams because you cannot resolve the different paths, right? So these multiple antennas can be only exploited to increase your link budget for beamforming, okay? But I think that's the best thing to do on a channel that is very weak in terms of the link budget. This is from a quick thought, but I guess it makes sense, right? And then you were asking about, so that was for the satellites. Then maybe you were asking about UAV connected to the terrestrial network. Same thing, I guess. You cannot send multiple streams unless the channel is line of sight, but there is also some significant reflected path. So the channel is mainly line of sight, but if the channel matrix rank is not 1, there's some other eigenvalue that is not 0, if you know what I mean, you can still probably allocate something on the second stream. Is this going to be done in practical networks? I don't know, honestly. But it could be potentially. There's something interesting I want to point out related to this. Maybe it's only partially related, but maybe you'll find it interesting, which is if you operate at very, very high frequencies, like terahertz, nowadays, many companies are thinking of terahertz or at least sub-terahertz. In that case, you have to work in line of sight, right? Because the propagation, if not, you don't reach. As you go to very, very high frequencies, the wavelength becomes very small. So the size of the antenna compared to the wavelength becomes huge, okay? Because you always need to think in terms of wavelength, not in terms of meters or centimeters. And if you get close enough between transmitter and receiver, you get into a near field propagation region where things change significantly. It's as if the array curvature starts to matter. When you're far away, you see the array as flat, but imagine that you have an array that is enormous and you get really close to it. At that point, there is a curvature effect because you cannot assume the plane wave propagation anymore. You need to assume the spherical wave in all the details, okay, which usually we never think about. In that case, the channel matrix is not rank 1 anymore. Because of this curvature of the array, you have more than one, you can transmit more than one stream. So you can do MIMO in line of sight. So there's a new line of work, which I'm not personally leading, but some people in our group are, that is very interesting. Of course, it's not for UAV, okay, because maybe the UAV is too far for that, and for terahertz, maybe the wobbling will make it a bit impractical. But I just thought of mentioning and bringing it up because it's related to your question.
Thanks.
Thank you for your presentation. I really enjoyed it. Very interesting, actually, results and information. I have a question regarding to the interference suppression. I assume that it's digital beamforming, right?
Yes.
So you need the channel state information for from the other cells. So do you do complexity analysis, especially when the number of UV increases, or?
This is an excellent question, thank you. Yes, so in order, maybe I give a little background just for somebody who might not be as familiar as you with the topic. So in massive MIMO, you leverage spatial degrees of freedom. So by having multiple antennas and multiple radio frequency chains for each antenna, you have a certain spatial resolution which allows you to place multiple beams at once. So in theory, if you have n radio frequency chains, you can place n beams. Or you can suppress interference to n directions. So in the total degrees of freedom you have are no more than n, okay? So in order to place a beam or suppress interference, you need to know where to do that. Imagine I want to place the spotlight on that table. First, I need to know where the table is. So this is an analogy with what has to be done with a user. The user has to tell me, hey, I'm here, place your beam here. Or, hey, I'm here, please do not interfere here, right? So this is learned through channel estimation, okay? I need to acquire this channel state information. How is this done? In a TDD setup, because there's reciprocity between downlink and uplink, because they work on the same carrier, you can estimate the channel in uplink and then use this information in downlink. So the user will send a pilot signal or a sounding reference signal, and then you use this information for the downlink, okay? Why this? Because it's more scalable, because this scales with the number of users and not with the number of antennas. So, you know, for massive MIMO, the number of antennas is huge. If you do the other way around, it doesn't scale. You have too much overhead. Anyway, long story short, for your cell and for your users, this is easy to do because you know which users you're going to schedule in each time frequency resource block. And so first you ping those users and you tell them, okay, send your pilot, got it, okay, here's the data, right? But if you want to suppress interference to a user in another cell, you need to acquire the channel between you and that user, not between that user and the serving cell, between you and that user. This is typically not done because we don't need it typically. So the question, legitimate, absolutely, is do we need extra signaling? Yes, we absolutely need extra signaling. Maybe we need cooperation between like a cluster of cells where at least scheduling information is exchanged such that, and pilots are allocated orthogonally so that there's no pilot contamination, such that I can estimate the channel to that user. And so what did we assume? Now going back to our study, what did we assume? We've done several works in that respect. One work we did at the very beginning was to do blind channel estimation. So it will work this way. I have a silent phase. I just listen to transmissions in the environment. I receive the aggregation of signals. I calculate the eigendirections from this channel subspace mathematically, and then I don't know which user is which channel, but I know what the dominant channels are, so I suppress interference. I don't know who is there, but I know where I should suppress, and I do it. Okay, this was more of a theoretical. We thought about this for Wi-Fi, to be honest. Okay, but for a practical cellular, I think you need this coordination. So you really need to like. First, you need to estimate which user would suffer most from your interference, so you can focus on that. You don't need to suppress everyone. Just suppress the one that maybe you see in line of sight. For the UAV, it's very easy. Even just by knowing the angle, because the channel is dominated by the line of sight, you can do a very rough estimation, at least of the statistics of the channel and the covariance, just from the position. So I see it practical. I don't know to what extent you would agree with me, but it's possible to do that.
Totally agree. I think what you have said, it's kind of algorithm that you solve the problem rather than the whole users or UAV in the whole area, which is really, really nice.
Yeah, thank you.
I have another question which is related
Please.
to the same subject when you talked about the multi-user MIMO in the millimeter wave. It's again, it's the same issue. You have the complexity increases, and you need to not only digital beamforming, but also you need analog. So have you considered the hybrid beamforming or?
Great question. Yes. So for this work on millimeter wave, we've been doing it with colleagues from NYU in the US. We're talking world-leading people, experts on millimeter wave. And they also work with companies and they know at what stage the products are right now. What I understand is that MU MIMO is not being considered because you have so much band that you don't need to bother doing MU MIMO. You already have enough capacity. They're actually worried by other things, blockages, power consumption, and stuff like that, okay? So most of our work on millimeter wave considered SU MIMO, single user MIMO. Then this last result I showed was for a paper that we have at Globecom, was the first extension we did to MU MIMO to understand the effect of interference. And there isn't a lot, because at millimeter wave, you have quite a good cell isolation. So typically this interference suppression is not needed. It's not like sub 6 gigahertz. So it's much easier from that perspective. You have other types of problems, power consumption, beam management, and things like that.
Thank you so much.
Yeah, thank you.
In uplink scenario, because UVs can contact with many base stations, can diversity play a role in this scenario?
Okay, so if you understand your question, we are mostly talking about sub 6 gigahertz now, and you're saying in the uplink, a UAV transmits, multiple cells receive that. Can we exploit this? Yes, the answer is yes. I took that off from the slides because I had too many slides, but I wish I kept it to mention it to you. So this is something related to cell-free. I don't know if you heard about the cell-free architecture. So cell-free means that you have many access points. You don't have one big base station. You have many small base stations and many users, and every base station serves every user. It's not one base station serves one user, the other base station serves the other user. Cooperatively, they serve all the users. Mathematically, you can model this as a distributed antenna array. It's like one big brain behind many antennas that are all scattered around, but they act together. Of course, the fact that they are scattered around has massive implications in terms of signal processing, complexity, and performance. Okay? So this is the way we would implement what you just proposed. So one such user, in this case it would be a UAV, would transmit. All our distributed access points they're typically low power, small, and densely deployed, would receive, and then they talk to each other and they say, hey, I received this, hey, I received this, and then we just do joint processing. Maximum ratio combining, zero forcing, it depends on the level of complexity you want. And basically by doing this, there is no more interference. All the interference has been converted into useful signal. So the performance is fantastic. The problem is implementing it. So this idea has been around now maybe for about 10 years or yeah, something like that. And there are ways to do it more practically. But for UAVs, it's very complicated. Why? Because the cluster of cooperating access points for a ground user could be small. Maybe it's enough to coordinate 3 or 4 neighboring access points, and the other ones far away don't matter. But the UAV sees many. You need to coordinate a big cluster. You need a wired backhaul, high capacity, because these have to share the data, not just the signaling, the scheduling decisions. They have to share the actual data, right? The IQ samples, for example. So massive backhauling capacity. Plus, because the UAV moves, this cluster will have to be dynamically. So it's an interesting idea. We actually have talked about this in the tutorial paper with numbers, with results. But practically speaking, densification doesn't seem to be the solution for UAVs. Does this answer your question? No worries. All right, so if there are no more questions for now, I'll move on to the third part of the tutorial, and of course we'll have more time at the end if you wish. Unless there's something from the audience. No, right. Okay, so here I just want to bring all these pieces of the puzzle together and mention what I think could be a converged 3D network of the future. Of course, this is more speculative than what I've been talking about now. What I talked about now, I hope, is backed up by industry evidence and performance analysis. This is more imagination, but probably will turn into reality. So let's go back to the first image I showed at the beginning, but with more details now. This would be an integrated TN and DN architecture. If you attended my talk, you already saw this image this morning, but let me briefly go over it for those who didn't. I tried to put all the ingredients of my recipe in here. So this is the terrestrial network segment. So we have our good old base stations down tilted, but potentially we could have up tilted cells. You know, we already talked briefly about that before. Because if we want to serve UAVs, we could deploy a few of these just for the UAVs, okay? Then there's going to be emission problems in certain bands, of course. We could have the non-terrestrial network segment with satellites, hubs, maybe inter-satellite or inter-hubs links, as it was mentioned. And then we had the service link that connects the users, and we could have terrestrial users, aerial users, relays that relay to other terrestrial users, or UAV to UAV. Imagine a swarm of drones with the leading drone connected and the other drones following, etc. Then we close the loop with the feeder links to connect to an NTN gateway on the ground that connects you to the core. So once again, these are the type of platforms, all the devices that act as cells, and then we have different types of terminals with very different features depending on their size, their capabilities, the frequency at what they operate, the directionality of their antenna terminals, etc., etc. So everything is use case and application specific here. So talking about use cases, I wanted to mention 3 use cases that I think are representative. Besides, of course, the one of providing connectivity to the unconnected, which we're all very familiar with. Now I try to complement with other possibilities. One is critical communications. So, maybe I have connectivity, but there was a disaster, there was a fire, there was an emergency or something, and then I want to resiliently and rapidly replace that connectivity with direct access from space or even by a UAV, for example. This is one use case. Then there is massive IoT and immersive communications. So here, maybe I want to collect data from a lot of sensors, maybe in the ocean, in the jungle, whatever, okay? And then maybe I want to multicast these data to provide immersive experiences to users. Maybe they're wearing goggles, okay? Maybe the concept of the metaverse that some companies really believe in, okay? And so if I want to send the same to many, many users, this could be a way, because the non-terrestrial network cell has a huge footprint, okay? So I can multicast this. And the third use case, which I'm more familiar with maybe, is the urban air mobility one. So again, I'm going back to aerial now, aerial users. So if I imagine UAVs delivering goods, like delivery drones, or even delivering people, then the burden goes onto the network, because at some point I want these to be autonomously flying. So the connectivity requirements are going to be extreme if they carry a package, let alone if they carry people, right? And also if these people also want to be connected inside. Maybe you have a flying taxi, you connect to the flying taxi, and then you relay connectivity inside to the passengers, for example, okay, with Wi-Fi. So the network needs to be connected very reliably to this vehicle. Now, regarding this third use case, I tried to explain this today in my short talk. This is what I have in mind, and some other colleagues in the field also think likewise. I'm not the only one proposing this. And it's the concept of aerial corridors, or highways for UAVs, or UAV corridors. So right now we don't have many drones yet, but imagine a future where we're going to have many, many drones. It's not sustainable for them to fly wherever they want uncontrollably, right? At the beginning, I'm sure that when we started having the first cars, there weren't really any proper roads. You could just drive wherever you wanted, okay? When you're in the desert, there are not designated roads. You have some room, for making your own way, but not in the city, right? So I suspect the regulators at some point will have designed these highways. And they will not follow network constraints. They will follow safety constraints, architectural constraints, right? And then the network might have to adapt and cater for these highways. Not only that, they might change with time. Maybe a new building is made, and then you need to change the route. Things like that, okay? So the problem for us, somebody like me who's been, working on trying to provide connectivity to UAVs, we changed slightly, because in the second part of my talk, I really struggled to provide reliable connectivity to the sky, because I wanted any UAV, wherever it was, to be connected, okay? And that was very difficult. But what if I restrict the route to a specific region, like a pipe in the sky, okay? And then I just want to tune my network to cover that region and nothing else. Maybe this is more feasible, right? I'm aiming for something more feasible. So I'm thinking about rethinking the ground network design, the operation, and the optimization itself. So I want to show you now 3 possible ways of doing that briefly, okay? 3 possible ways. The first is to take the terrestrial network as we have it and to optimize it for these UAV corridors. This is the first way. So here I try to draw the UAV corridors, so these blurred green areas, okay? So UAVs fly there. I have my terrestrial network. Most of my cells will serve ground users, but some of them will be dedicated to cover the UAV corridors. So how can I optimize that? So we did a first study with a paper that we actually have to submit very, very soon, because the deadline is in like 2 or 3 days, which is like a mathematical framework. This is with colleagues from UC Irvine. Mathematical framework, which is based on quantization theory. We want to optimize the antenna tilts, okay, for all the base stations. We want to optimize these antenna tilts to cover both the ground and the UAVs, given where the corridor is. So I give the algorithm where my corridors are, and the algorithm should optimize all the tilts, okay, to serve both the ground and the corridors. And so we want to do this, of course, with the proper modeling, with the proper deployment, the antenna pattern, and the proper propagation channel model. So some preliminary results. Here I'm optimizing for receive signal strength, okay? Of course, you might want to optimize for SINR. The framework still works. Just the maths get a little bit more extensive, but it works. So basically, we have a certain performance function, which is the receive signal strength on the ground and on the corridor. And we have to give a weight, right? Because it's a trade-off. We can give priority to the ground. That means I set my parameter alpha to 1. That means priority to the ground. Alpha equals 0 means priority to the sky only. And alpha 0.5 trades off. So both priority, equal priority to the ground and to the sky. You can just vary this parameter in the framework, okay? And this is the tilt, antenna tilt, vertical, for each base station. So we have 57 base stations. It's 19 deployment sites, 2 tiers of cells, each one 3 sectors, 19 by 3, 57, okay? So what happens? When you cater for the ground only, all the tilts are negative. They're down. That's the case in green. All the tilts are negative. When you cater for the sky, blue, some tilts, most of the tilts are 0 because you don't care about the ground user, and some are up for the drones. The trade-off is alpha 0.5 when you want to cover both, the red one. Then some base stations are facing down, most of them, but some are tilted up to cover the UAV corridor. So it makes sense. It's just that you need an algorithm for this. You cannot do it manually because it's a combinatorial problem. It's NP hard. Okay? Right. So here I just want to show you the cell partitioning that comes out of that. So if you work in telecom, you know that on the left, you expect to see hexagons, okay, for the cell partitioning. But if you tilt up some cells, you create strange patterns. You see those small colored regions. So the cell partitioning changes because you have optimized for the corridors as well. And these are the 4 corridors we considered. These are the 19 base stations. Each one has 3 sectors. These are the corridors. And the color means a certain cell. So these 3 bits are set by a certain cell, the ones in red by another cell, and these probably by this cell tilted up. The result is not obvious, meaning it's not so easy to do it by hand. You cannot do it by hand. It's a combinatorial problem. So the algorithm seems really to work well. And of course, just to conclude, what is the performance in the end after I do this? So this is the receive signal strength. Don't get confused by these curves. I'll show you what it means. For the UAV, if I don't care about the UAVs and I only care about the ground users, I get this receive signal strength, this blue one. And instead, if I optimize for the UAVs, I get this one. And if I optimize for both, I get the red one, which is almost optimal. So it's pretty good. And then the question is, yeah, I boosted the UAV corridor signal, but did I pay a price for the UAVs, for the ground users? No, not so much. Because I went from the green one to the red one. So really the price I pay for the ground users is not so large. So long story short, the algorithm can reach a trade-off between covering the ground and the corridors. This is really our preliminary work. We want to extend this considering other things, but just wanted to show you that it's promising as a mathematical tool, okay? The second thing now, so this was, I have a ground network, I optimize it for the drones. Now, I rethink the network by adding base stations for the drones. Okay, this is the second approach. I presented this morning. So now I'm imagining a hypothetical setup with 2 operators. A terrestrial operator that has rented the sites, MNO-T, and then an operator MNO-A that wants to reuse the same sites, but imagine that this base station is up here, and the same spectrum. So I want one operator to serve ground users, one operator to serve UAVs, using the same spectrum and the same sites. There's going to be interference. So I'm greedy. I want to use the same spectrum to serve all these 2 populations of users, but is it going to work? So we run this study. We assume massive MIMO with 0 forcing, and massive MIMO with zero forcing and interference suppression. And long story short, let me just go through this with you, okay? This is the SINR as I deploy more and more rooftop cells for the UAVs. So this is the intersite distance. Infinity means there are no cells, and then I go more and more dense, so I deploy more and more. So, and this is the SINR for the drones in blue and for the ground users in orange. At the beginning, when I offload the drones to the new operator, I go worse because they're interfering to each other now. Before they were separated because one operator was handling both. Now the two operators are handling them separately but in the same spectrum. So it gets worse. But then as I deploy more and more, things get better again because now there are many cells. The UAVs can see many cells nearby and they can also lower their power so they interfere less to the ground. So just to be brief, there are many trade-offs going on, and if you do the deployment correct, the two operators might coexist, okay? So the UAVs can lower their power and interfere less to ground users. And you might wonder why I have two different colors. One is with zero forcing, and one is with zero forcing plus intercell interference suppression, the thing I was mentioning before. Obviously that helps. You always reach better 95th percentile SINR gain. So interference is the key to be managed there, and if you manage it properly, you could have two operators coexisting. This is the main result in a nutshell. This was SINR, and if I think about rates, the gain is even more, because this is just the SINR, but now I have two operators reusing the same spectrum, so in terms of capacity, now I'm going to see the gains. And here are the gains. These are the rates for the UAVs. If I have only the terrestrial operator, I get this, okay, under different setups. And then if I have more and more up-tilted cells, I immediately see the benefit. If I don't have enough, the interference is still penalizing me, but then as I have enough, I see the benefit. So there are trade-offs there. The answer is not straightforward, okay? And yeah, we also did this on millimeter wave, and to see what happens when I do the same thing, the two operators, but now operating on millimeter wave, and I also see benefits. I also see benefits because as I deploy more and more millimeter wave cells, the number of UAVs that are connected to this rooftop cells increases. This means that more and more drones start to be offloaded, this solid color, and they are in line of sight. So I can offload traffic. When I offload traffic, I gain in capacity as always, because I'm reusing the same spectrum twice. Okay, it comes for free if I can manage interference. I really don't want to be too heavy on the details, but when I finish speaking, if you're interested in something in particular, we can go back. Okay, I know that it's quite dense in terms of content. Okay, and this is how many links you see in line of sight, and you see almost all the links in line of sight once you have so many cells, because the UAVs have so many different options to connect to, not only the down-tilted cells, but also the up-tilted cells. So you go from having 70% or 80% of them in line of sight, depending on the height, to 99% in line of sight, okay? And this is what I said before, that as I increase my density of rooftop cells, I improve my SNR, but the main gain is in the capacity gain, because I can offload the traffic. Okay, so now the UAVs with a high uplink video streaming, they're not eating my resources anymore from the ground users, they're offloaded to new cells. And this is the last part of the tutorial, okay? Is the third case. Now I'm bringing the satellite into the picture. So now my terrestrial operator, instead of partnering with the aerial operator, hypothetically, it's partnering with a satellite operator. So the satellite operator is probably serving the unconnected, but because it's an orbiting constellation, the satellite will inevitably also be on top of an urban area. So the question we ask is this helpful? Can I use it for something? And this something, in our example, is to serve some very high UAVs, eVTOL, electrical vertical takeoff and landing vehicles, okay, for example, for advanced urban mobility. These are supposed to be at 1,500 meters. So again, I study what happens, and I consider those key parameters that I explained at the beginning of the talk, the frequency reuse factor of the LEO and the elevation angle of the LEO. So what happens? So when the eVTOL is connected to a standalone terrestrial network, the SINR can get pretty bad depending on how many eVTOLs I have in a cell, because even a massive MIMO array cannot spatially separate them, because I see them all with the same angle and there's too much interference. So the more I have, the more this degrades, and I start having a bit of outage. Instead, if I offload them to the MNOS, which is the satellite operator, the values of SINR that I see are pretty decent, and they depend on the frequency reuse factor that I'm using. Remember, frequency reuse factor 1 means aggressively reusing the frequency on all the beams, so there's interbeam interference, so the red is lower. Blue is more conservative. Adjacent beams use different frequency, so there's no interference. But I sacrifice the band here, because I only use 1/3 of the band. And the elevation angle is something else that really matters, because when the satellite is on top of me, things are very good, but then as it moves, I lose. You see, there's quite a big gap already from 90 to 87, okay? So MNOT might struggle if these eVTOL proliferate, and then a solution could be to offload them to the satellite operator. It's just one example we wanted to test of a potential application of LEO satellites in urban areas where there already is terrestrial network connectivity, to see if they could be useful somehow. And we also considered the data rates, and the data rates could be quite low or quite high, depending on how many of these I have in a cell, because then they have to split the band between them, okay? Right, so here is some references of relevant papers. It's a non-exhaustive list by any means. These are papers that I know of the last couple of years. The first two are my papers, of course, and basically they're the most related to this talk in case you're interested into more details. But all the others are also very relevant to what I talked about. And so just to summarize, you know, the title of the talk was 3D Opportunities and Challenges. So I think that this 3D network is coming. I don't know how long it's going to take, but it seems it's coming. As an integrated vertical wireless ecosystem, let's say, it brings huge opportunities to connect the unconnected. That is clearly the #1 opportunity we have. It is also going to open new markets, hopefully, but perhaps also to hyper-connect the already connected. And this could be another use case of the same technology. So I really think this could bring added value, and it could enable new services. For example, area services, which has been the focus of my talk today, but there could be others. It brings challenges as well, so it brings research problems that we're very excited to be working on. What is causing these challenges? The architecture is extremely heterogeneous. It's heterogeneous in terms of services to be provided, in terms of the spectrum to be used, in terms of the capability of the devices, and in terms of the ownership of all these nodes in the network. And the questions that you have asked throughout my presentation really touched upon all these 4 aspects, I think. So I really think that we agree on that. And so what is the challenge for us is to provide a unified optimization of all these deployments and some smart algorithms that can really run this network as one. This would really make the most of it. I don't know to what extent it will be possible due to political, commercial, regulatory interests, but this would really be the holy grail, right? And so my hope is to make this 3D wireless network of tomorrow and to work together towards that, because I think it's essential. I really echo the words of some of our speakers yesterday and today that really this requires a joint effort from many, many actors, hopefully including academia as well. Thanks very much. If you have any questions, I'll be delighted to take them.
Yes, thank you, Giovanni. Thank you so much. I think we have room for a couple of questions. If you have any questions maybe I can. Any question from the audience here at the room? Or, yeah, I think yeah. Yeah, I think we have a question here. Can conditional handover be used? Okay. Okay, then what interference management approach expected in multi-tier NTNs, particularly in terms of spectrum allocation?
Very good question. Yes, somebody from the audience asked this earlier regarding what frequencies and, you know, if we need coexistence, etc. So my answer was that it really depends what we're talking about. As far as I'm aware, for NTN LEO, they're expected to use dedicated bands, so not the same as the terrestrial band. So in that case, to think about using the same spectrum and smart ways of coexistence is a little bit of it's a bit far-fetched, you know. Although research in that regard would be welcome, of course. In terms of millimeter wave, it seems Dr. Abdallah suggested that an agreement is yet to be reached, probably. HAPS is probably the technology that might be using the same frequencies as the terrestrial network, and in that case, then you might need some coordination. I think the distance between HAPS and an urban area, for example, has to be considered and has to be monitored.
Yeah, I think the second question is line of sight propagation means less selectivity in frequency. Does that mean we might consider forgetting multi-carrier communication schemes at OFDMA? I think this is quite a good question, actually.
Yeah, I'm not sure about the multi-carrier. I think multi-carrier will still work, but this is related to the question I received in terms of doing multi-user and multi-stream transmission and line of sight. And the answer we gave was that in some scenarios from satellite, you might not even want to think about multi-stream because really your priority is to close the link budget. So any beamforming gain, you might want to use it. So you don't want to trade off beamforming gain for multiplexing gain. In other scenarios like UAVs, well, yeah, probably you have to restrict yourself to single stream unless you have enough scattering on top of the line of sight that allows you to do a decent, maybe to send a couple of streams at once.
Yeah, the last question is what RF interference issues do you anticipate for multiple satellite constellations?
This is a very valid question. I'm not an expert to answer this question, but I think it's really important. I think this has to do with inter-operator or inter-constellation interference, especially if they are located at the same band. I really don't know what the status quo is right now, because the current constellations we have, I'm not sure they're already using the bands that are foreseen. Maybe that some of them have proprietary solutions.
Yeah. I think this might be a nation by nation based. I think so. If FCC allocate frequency to Starlink, they will make sure that they don't give this frequency to the Amazon or Jeff Bezos, the company Kepner. But still, yeah, I think it's an open issue and it needs to be solved. I have a question actually. I mean, we have met a guy from SpaceX just in the lunch, and he said that they have initiated generation 3 of their constellation, which is interlinked through lasers. And he mentioned, I mean, the width of the beamform of this generation is 4 kilometers actually, which is quite not that much large. I think this might solve the problem. Yeah.
Perhaps they're using millimeter wave frequencies, and therefore they can have more directivity. Yeah. Perhaps I heard the same from people from Kuiper or somebody who collaborates with them. Yeah, that's the idea. I think everybody wants to increase the rates. The only way, by physics, is to increase the spatial reuse to get the cell splitting gains. The same thing we did when we started talking about small cells, right? So I suppose they're going into this direction.
Yeah, I think the question from myself, actually, Giovanni, is it seems to me that harnessing the mid-layer is quite a hot topic now in research. It seems that the space layer is going well when it integrated with the terrestrial layer. However, still we are facing, or we still need to solve the challenges between the mid-layer and terrestrial networks.
When you say mid-layer, you refer to aerial?
UAV, and
yes.
Most of the paper that we got related to this issue, actually.
Yes. I think HAPS could be a very good solution. Of course, I mean here, depending on whom you speak to, there's interest behind it. Of course, I'm kind of like technology neutral because I come from academia. I see advantages in both solutions, right? So of course, HAPS might be quicker to launch. Let's say they might provide higher rates if their footprint is smaller than a satellite. Again, because there's fewer users to split the data rate with. Maybe they have also they have good features in terms of not leaving any space debris, for example, not causing any light pollution in the sky, and of course they have other technological hurdles to be overcome at the same time. Again, we from research and academia, obviously not having commercial interests behind, we see all these technologies as complementary, not as competitive. And if you see, there's been a lot of work, not just from myself, but by other great researchers in the field, where we have this vision of a multi-layer architecture where these technologies complement one another. Of course, to really make this work jointly, you probably had to overcome all these commercial interests, but perhaps if these platforms are leased as a service to operators, then maybe the operators could leverage this, could apply this vision of a joint operation. What do you think about that?
Yeah, I think as most of the speaker has in this event has actually emphasized on the fact that we need to complement, not to compete, actually. And the business model you said, I think, will be mostly used when the satellite or UAVs or HAPS operators will lease their services and connectivity as a service, maybe to the mobile operator. Thank you, Giovanni. Thank you so much. Giovanni will be also with us tomorrow in one of the panels. So we got much of Giovanni, and thank you so much and keep you busy all the days. Thank you. Thank you, guys, and let's have another warm applause to Giovanni. Thank you.
Thanks very much. I really appreciate the invitation and the participation of the audience. I know that we've been listening to a lot of talks. We might be tired at this time of the day, but you made this interactive, which was really pleasurable for me. Thanks a lot.